Hi everyone, welcome to CSM walkthroughs for EECS 16B. This is week 3 and we will be covering question 3, part A for this video. I'm Jiu. Okay, assuming that you already have an intro on transfer functions, I will go over part A. So, considering the following RC circuit, we first need to write out our transfer function h of j omega. Here, h of j omega is equal to h of omega. You can use whatever notation you're comfortable with. Now, we see this RC circuit and we realize that it's actually a voltage divider. So we use our voltage divider equation that we are comfortable with. And where the voltages are replaced with the phasor versions and the resistances are replaced with the impedances. Now, we realize that if we divide both sides by V input phasor, then this part here becomes V out over V in, which is equal to h of j omega. Therefore, we just need to solve for this. But this is just by the forms of impedances of the resistor and the capacitor that we already know. So we simplify this by multiplying j omega c on both the numerator and the denominator, and we get this. So that will be our transfer function. Now, for omega approaching 0, we will have this fraction where this part is approaching 0. And that would mean we have this. So as omega approaches 0, the magnitude of 1 is just 1. So we will have our magnitude of the transfer function as 1. This means that our V input is almost equal to V output when we have a small omega. Okay. Now, let's see when omega approaches infinity. In this case, I will just bring this over to here. Okay. Due to technical difficulty, I'm gonna pause this. I'm back. Okay. So we were solving for the magnitude of our transfer function as omega approaches infinity. And in this case, I'm going to use this. The denominator goes to infinity, meaning the whole thing goes to 0. So in this case, our magnitude, the magnitude of 0 is just 0. So the magnitude of our transfer function is 0 as omega goes to infinity. Big omega. And this means our V out phasor is equal to 0 for a big omega. Finally, let's calculate the cutoff frequency. Remember, for a cutoff frequency, we want to find omega when our transfer function equals 1 over root 2. So we will denote this cutoff frequency as omega c, sub c. Okay. We know that our transfer function is just 1 over j omega rc plus 1, equating this to 1 over root 2. We want our j omega rc to be 1. Okay. Oh, sorry. Plus 1 equals root 2. So we want the square of this to equal 2. So that means our okay, my bad. We want the magnitude of our transfer function to be 1 over root 2. So that means our magnitude of the numerator over the magnitude of the denominator is equal to 1 over root 2. But our magnitude of the numerator is just 1, which is equal to this. So we just want this part here to be equal to root 2. And this part here is this. And this is equal to root 2. So we want our omega rc, the whole thing squared, to equal 1. So that means I will use our cutoff frequency notation for all this. So that would give us rc square rooted. Yeah. So I missed the squares here. So that would just be 1 over rc. So that's all for part 4 of subpart A of question 3. And that's all for the part A. One thing to notice here is that as the frequency approaches 0, so for a small omega, we have our output that is almost equal to our input. But for a large omega, our output is 0. This basically means that this circuit here is a low pass filter, which means that when we put in a large frequency, we don't have any output. When we put in a small frequency, we have the input voltage passes through. Yeah. So that's all for part A.